Hey there, welcome back to Short Take 331. Today we're going to continue our discussion of Fourier series generalizations and applications. And if you recall, last time, so in part 1, we started talking about diffusion in 1D. So we started looking at trying to solve this kind of partial differential equation with one derivative with respect to time, two derivatives with respect to space, and some diffusion constant in here. So we're trying to solve for this function that's a function of space and time, so f of xt, with some boundary conditions that the function vanishes at 0 and vanishes at L. So this is a region of interest for some L that could be any number we want in principle. And of course, we're going to have some initial conditions as well. So if we have spatial derivatives, we need boundary conditions. If we have time derivatives, we need initial conditions. And so we're going to assume that this function f of x is given for all x in the relevant region of interest at time t equals 0. And of course, these boundary conditions hold at all times. And what we saw last time in part 1 was that to solve this problem, one way to proceed is to start looking for eigenfunctions of the second derivative operator and with the proper boundary conditions. And so you have then this is your secular equation for the eigenfunctions of that second derivative operator. And what we know also from previous videos is that those properly normalized wave functions, or functions, eigenfunctions, I should say, are these phi n of x. They're given by square root of 2 over L sine of n pi x over L. And the lambda n's are minus n pi over L squared with n equals 1, 2, 3, and so on. Again, I always emphasize this n does not cover 0 because for n equals 0, this function completely vanishes, and so it's not a proper eigenfunction. Eigenvectors in general have to be non-vanishing. And also, we don't cover negative ones because the negative ones don't give you anything new. It's the same eigenvalue and technically the same eigenfunction. If you just flip the sign here, it's the same vector, effectively. So n goes then from 1, 2, 3, and so on to infinity. So this is going to be our eigensystem. And so based on that knowledge, we propose a solution for f of xt of this form, where we separate the time part and with some function that we have to find, c sub n of time, and then we multiply by our eigenfunctions phi n of x, and we sum over this index from n equals 1 to infinity. So these are things we need to find. These are coefficients that we need to find of the expansion of this function in terms of eigenfunctions of the second derivative operator. And that simplifies the problem, because if you take that function and you submerge it into our differential equation here, then you get that the time derivative goes right through and hits this constant, well, it's not a constant, of course, it's a function of time, this Cn of t. It doesn't affect the phi n of x. And on the right-hand side, the spatial derivative goes right through the constant and it hits this function of our basis of eigenfunctions, this phi n. Now we know how the second derivative acts on that. It pulls down to lambda n, and so its action on on the spatial part is very simple. It's just a constant lambda sub n. If we put this on the other side of the equation, then we can summarize this result in this form. So we have the sum from n equals 1 to infinity, this parentheses times our functions of our basis, all equal to 0. Now these functions are all linearly independent, and so it must be that this parenthesis vanishes. And this is how we derive the equation that I showed last time for the time derivative, or rather the time dependent part of the expansion, which I didn't tell you how to derive last time. So this is how you derive that equation. And so now we have a very simple differential equation. It's a first order differential equation. It's an ordinary differential equation. Even though I'm writing partial derivatives here, there's only one variable that appears in the problem. This is just time. And so all we need is the initial condition. Now this initial condition that we know from up here, which is given to us, f of x comma 0 for all x in our domain, it simply becomes this expansion. So we're using the same expansion we proposed before. And now we're evaluating at time equals 0. So we can assume that if we know that f of x comma 0, then we know also these coefficients. These are kind of be assumed to be known by the information given as a statement of the problem. And so if that is known, then we know how to solve this equation for all n's and for all times. So it must be that the function that solves this problem is simply Cn of 0 times this exponential. Indeed, if you take a derivative on both sides of this equation, you see that it solves this equation and it has the right initial conditions, and that they give you Cn of 0. And so the 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 result then is that once you insert the lambda n as minus n pi over L squared, then you have correctly a decaying exponential as a function of time. You wouldn't expect a solution where the exponential blows up, so it makes sense that these eigenvalues are purely negative, and so these lambda n's then have this sign and this n pi over L quantity squared times time, and that's the solution then for a time-dependent piece. And so that's at that point that we got to put everything together, and so the full solution for our problem is f of x comma t, sum from n equals 1 to infinity, this constant evaluated at time equals 0, our exponential, our decaying exponential, and then the functions of our basis. And I think in the previous video I omitted by accident this normalization coefficient, but other than that, it's basically this, all you have is this. And so these initial conditions determine the shape of the solution. So once you set these initial constants, then you can run the movie forward as a function of time, and you can investigate any position in space in your domain that you might want. This then is just the initial condition. This is our differential equation talking to us as a function of time, and for the spatial part we have these eigenfunctions of the second derivative operator, which of course incorporate also the boundary conditions. So the solution always vanishes at x equals 0 and at x equals L, and at t equals 0 this becomes 1, and you recover the solution that you would expect at t equals 0, so it obeys the initial conditions as well. And so this is all is well with this solution. We will see in a part 3 or a part 4, if we get to it, that you can pick an initial condition and plot how it evolves with time in all of space, and so we'll see that later. But for today, what I wanted to discuss is what happens when you go to higher dimensions, and it's a generalization of what we've been doing. So suppose we go to 3D and our diffusion is isotropic, so this constant d doesn't depend on the direction, so isotropic means the same in all directions, then this will be our differential equation for diffusion. And no matter what's diffusing, that's described by f, but this is this f, such an f should obey this differential equation, where this nabla squared is the Laplacian operator, which is the sum of the derivatives in the x, y, and z directions. And of course, if you were in 2D, then you would drop the z derivative and you would have just the x and the y part. Now, depending on the boundary conditions, you may want to switch coordinates. So here I use Cartesian coordinates to express the Laplacian, which is what you would do for a cube. And so if you had a cube or a cubic type of geometry of side L, as I've pictured here, then these Cartesian coordinates will be the right ones. And suppose our boundary conditions are that the function has to vanish on the sides of the cube, on the faces rather, I should say, the faces of the cube at all times. And suppose we're given the initial condition f of r comma 0 for all r inside the cube, then time equals 0, and so then we have the information we need to solve the problem. And it turns out then that the eigenfunctions of the Laplacian in this geometry with these boundary conditions are given by this. They're given by a product, a separated product, phi n1 of x, phi n2 of y, phi n3 of z, where these phi's are the same phi's that we described in 1D. They're square root of 2 over L, sine of n pi x over L, and so on. And the lambda n's are the sums of the corresponding lambdas for each of these eigenfunctions. And so basically the solution in 1D allows us to solve the problem with the generalized geometry now that it's a cube, or it would be a square in 2D, just by forming these products. And of course in 2D it would be a product of 2 functions instead of 3, and a sum of 2 eigenvalues instead of 3. Repeating the exercise then, we propose this function, we end up with the same differential equation for the time piece, and the role of lambda is played by the sum of lambdas, and here then the time part is then the time, the initial condition times e to the minus d pi squared over L, the sum of the indices n1, n2, and 3 all squared times time. And so that's the time-dependent part. And if you insert the time-dependent part in your solution, then you arrive at a form that you can write in this way. You can write as a sum over all the indices, n1, n2, and 3. They start from 1. Each of them starts at 1. They all go to infinity. There's this coefficient that gives you the initial conditions. And then there are these functions which I wrote in a compact way, which basically amount to the solution in 1D, which you would have. You have here fn1x, fn2y, fn3z, all time-dependent. And then the time dependence is captured by this exponential as before, where this n, you have to insert the n corresponding to the particular direction that you're looking at. But this is the generic function of f, the generic form of f, with the eigenfunction of the corresponding to the spatial part as well. And that would be the end of the problem, or rather the statement of the solution, given whatever it is that we're given for the initial condition. Again, this function automatically satisfies all the boundary conditions and so on and so forth. One must just be given what the initial condition is. Now, if you change the geometry, that will change everything. So you have to really pay attention to the geometry when you're trying to solve this kind of problem. Again, the generalized Fourier series using eigenfunctions of part of your operator will always help you, but you have to pay attention to the geometry. So here in the case of a sphere, we're going to switch to spherical coordinates. So suppose you have then a sphere of radius r0. Let's assume this is a sphere, my very simple drawing here. And we assume that the function evaluated on the surface of the sphere is 0 at all times. So suppose that we want that instead of having then a cube or a square, then suppose we have a sphere. And of course, you can also generalize this to a two-dimensional case of a circle. The coordinates x, y, and z transform into our spherical coordinates r, theta, phi by these rules for x, y, and z, which I'm sure you've seen before. And then what we need is eigenfunctions of the Laplacian with these boundary conditions, that f of r comma 0 is equal to 0 and at r equals 0. In fact, this should be t, this should be time, this should be f of r comma time equals 0 at all times, not just at the initial condition, but at all times. You will find this fixed in the PDF version of the notes. Now, we need eigenfunctions then of the Laplacian with those boundary conditions, and it turns out that they take this form. So there's a part that depends on the radial coordinate and a part that depends on the angular coordinates, theta and phi. There will be indices n associated with the radial part, and then L and M, which are typical indices associated with these spherical harmonics. These are going to be our spherical harmonics. If you want, you can take this as proposing this form for the solution. And here we're going to index n with 1 and above, but the L part starts at 0, 1, and so on and so forth, and M can be from minus L to L. So why do we choose this form, the spherical harmonics? Because it turns out that the Laplacian applied to any function phi will have a radial part like this in spherical coordinates, and then 1 over r squared and a purely angular part. And the spherical harmonics have this property that when you apply that angular part of the Laplacian to the YLM, to the spherical harmonic, you get minus L plus 1 times the spherical harmonic. So the spherical harmonics are eigenfunctions of the spherical part of the angular part of the Laplacian in spherical coordinates. Here this is true for L equals 0, 1, and so on and so forth to infinity. M goes from minus L to L. And so if we insert our proposed solution of this form into our equation for the eigenfunctions of phi, then you will obtain that the YLMs basically will go right through. So the radial part doesn't touch the YLMs at all. And then when the angular part hits that part, then you get the minus L plus 1 factor, and then so basically it factors out. So once you get that, it factors out of the problem. And on the right hand side, you get lambda times Rn YLM. So this part that I underlined here completely factors out. You can cancel it, and then you obtain an equation for only R sub n, so the radial part. So then because we knew what we were facing, we knew our geometry, then we proposed this solution for our eigenfunctions, and indeed that's the trick. All we need to do now is to find these functions R sub n that contain some index that we haven't discovered yet what it is. There's the eigenvalue that also we haven't discovered what it is, but we know that there's this L plus 1 part coming from the spherical harmonics. This is a second order differential equation, but it's an ordinary differential equation for Rn. It's linear as well in Rn. So this should be solvable for us or by us. And remember, we have to satisfy that on the sphere, then we have to have that the boundary condition that on the surface of the sphere, the Rn vanishes. We also want it to be regular at r equal to 0. And this is important because the solutions to these types of differential equations will often have singular parts at 0 or at infinity or at some point. And so we want to then ensure that our solution is regular at r equals 0. It turns out that's what will happen. There will be solutions to this equation that will be regular at 0 or singular at 0. Well, we want our solution to be regular. We don't have any reason to believe that our equation should give any kind of infinity at the origin. And so we want it to be regular at r equals 0, and we want also to vanish. We want it to vanish at r equal to r0, so on the surface of the sphere. So assuming that we know this r sub n, that we've solved the problem in the region of interest, so for the radial coordinate between 0 and r0, then we can repeat our previous derivation or the previous steps that we saw before, and then the full form of our solution will be the function of rt, and it will be a sum over these indices n, l, m. Again, we haven't discovered quite what n has to be. I've indexed it from 1 to infinity because I know what's coming, but we know about l and m, and so then there will be some initial condition, and there will be this exponential part controlling the time dependence, and then there will be the product of our Rn of r and ylm of theta phi. Now here I also said we haven't discovered yet what this lambda have to be. Because of the boundary conditions, it will turn out that these lambda are quantized, of course, and they're quantized with this index n. But we do know that there's no reason for this function to blow up at high times. So we expect this to be diffusion, and diffusion processes decay with time. They don't blow up with time, unless you run them backwards in time, of course. But if you run them forwards in time, then you would expect this exponent to be negative. And so we expect this lambda to be negative. And so we're going to think about this as a lambda as negative, and so we're going to parameterize that with a minus k squared, and this will be convenient for the future derivation that we're going to see next time for some k that we haven't defined. So this k is as unknown at the moment as this lambda, and we'll have to figure it out when we solve this problem, so this equation with these boundary conditions. I anticipate that the solution to this equation is going to be something called a spherical Bessel function. Nothing to be afraid about. It will have to obey these boundary conditions. We'll figure that out, but I'll leave that for next time. I hope you enjoyed this video. I hope it was instructive. If you find it helpful, please consider liking and subscribing to the channel. And as always, if you're looking for a tutor in physics or math, in English or in Spanish, you can contact me at shorttext331@gmail.com, or you can leave a comment in the comment section below, and I'll get back to you. And I'll see you next time with the continuation of this derivation and more information on how to use Fourier series to solve these boundary value problems which appear all over physics. So I'll see you next time.